Thanks, Ian. It's a pleasure to be here, and I'm looking forward to this talk because it involves doing something that I've always wanted to do in a talk, and that is to do an experiment live with real data and real analysis using some mechanism. And of course, it's very hard to do a physical experiment live. You have to set up physical things, and they have to work. They have to work the first time, and you have to have good measurement systems and all that. But if you're doing an experiment with a computer, things are substantially simpler. And so, and in fact, since I'm talking about deterministic experiments are typically done using computers because you can make computers where there's no random error from one experimental run to the next. So I want to talk about doing computer experiments and what is alike and what is different about those kinds of experiments versus doing experiments in the physical world. So my plan for this talk is to to introduce an internet-based simulator. And this simulator is of a typical garden sprinkler, you know, the kind that rotate like this and they move down the hose and spray a lawn. And what I want to use this simulator to do is compare various design and analysis strategies for the various kinds of designs that one might consider using for deterministic simulation. So I talked about already briefly about the fact that computer experiments and physical experiments are different. Computer experiments are comparatively fast because they don't involve physical setup, although even though they're fast, it often takes a substantial amount of computer time to do one run. Whereas in a physical experiment, you may have to build a prototype of something that hasn't ever been built before, and that can be an expensive proposition, so it's costly. But on the other hand, once you actually build something and use it, there's a substantial amount of empirical validity to what you just did because it's real. Whereas, although computer experiments are fast and cheap, there's a big question mark about whether the model that's in the computer, that black box that the computer is representing, is actually accurate description of the real world itself. And that you have to take on faith, or you have to do validation experiments to calibrate the physical and computer experiment. I'm not going to go there today. There are lots of real applications of computer experiments. Circuit simulation has been used since the 80s and has been a large part of the huge improvement in the speed and the reliability of computers. Stress analysis for bridges or other kind of mechanical devices is also done using finite element analysis. That's a kind of computer simulation. Hurricane tracking is done using computer simulation models. And fluid flow around a barrier is another important thing. I'm sure that, well, I won't mention one of our customers that uses a lot of fluid flow stuff. Okay, so how are computer experiments different from experiments in the real world? Well, the first thing is that in the real world, all observation involves noise. It's unavoidable. It's the nature of real things. But in computer experiments, you don't have to worry about noise because to a large degree, because if you create the same initial conditions, you're going to get the exact same response. So if you think about Fisher's main principles of physical experimentation, one of them was you need to replicate runs because by replication you can get a model-independent estimate of the noise. And you need to randomize the order of runs because by randomization, you avoid biasing by lurking variables. In computer simulations, neither one of these things is applicable, so you don't have to worry about those things. Secondly, though, because computer simulations are often built around solutions to differential equations, we imagine that the functions underlying a computer simulation may be substantially more complex than what we think of when we're modeling a physical system. And so it may be that low-order, first and second-order polynomial approximations are inadequate to describe the system that we're looking at. And so we want a design that's capable of being more flexible than just being able to fit these kinds of low-order polynomial approximations. The other thing about computer simulation experiments is that since there's no noise, there's no variance. The purpose of designs like d-optimal designs and i-optimal designs is to minimize the effect of variation in the responses onto variations in the parameters of the model. If there's no variation in the responses, then you don't have to worry about variation in the parameters. But what you do have to worry about is the relationship between the model that you have and whatever is in the computer. These designs, like what would be produced by the custom designer in JUMP, are meant to reduce variation, but we don't have variation to reduce. So we need a different kind of approach to computer experiments than the variance optimal designs. Well, why design computer experiments at all, though? Because, can't you just do them all? Do all the runs that the computer can do? Well, if your computer is extremely fast and your simulation is short time, you can do substantially more runs than you could do in a physical experiment. But it's often the case that computer simulation models may take hours or days to run because they're trying to do something very difficult, like model a chemical reaction with a million particles interacting. And if you want to follow that through time with short little increments of time, then computer time can take a long time. And then another thing about computer experiments is that because they're computer experiments and because you don't have to carefully set every knob and dial on a system in order to, by hand, to make sure that each run is set up correctly, you can have computer simulation kinds of experiments that involve dozens or even hundreds of variables. And that's not feasible in the real world. If the simulator, though, takes a long time to do its work, what you would like to be able to do is develop an experimental program so that once you are done with that program, you would have a model that would be adequate to describe the behavior of the system, but where the predictions are much faster than running a simulation. And also, if you're familiar with the profiler in JUMP, the ability to play with the curves and move things around and develop intuition about the behavior of a system is a lot easier if you can do that in real time and interactively. So what do you want? So basically we have the real world, we have the computer simulation, and then we have our surrogate model of the computer simulation. What we want is that surrogate model to be close enough to what's really going on inside of the machine so that predictions that you make with the surrogate model adequately approximate the actual observed simulation result. And then you want the surrogate model to generate predictions almost instantaneously, whereas the computer simulation might take hours. So the standard surrogate model, and maybe I should say the standard design before you get to the model, this standard design is some sort of Latin hypercube design, and the standard model is a Gaussian process model. If you look at the literature of computer experiments from the late 80s on, probably 99% of the actual reported applications use that combination, Latin hypercube designs and Gaussian process models. So of course, in JUMP, there are Maximin Latin hypercube designs, and we also have Gaussian process models. That's an alternative. There are some very strong pros to Gaussian process models. They're very flexible, so they can describe quite complex behavior. If you have 10 factors, then the Gaussian process model only involves 12 unknowns, the number of factors plus 2. So the number of parameters that you're estimating is relatively small. And one final thing that engineers tend to like very much is the fact that at each point where you're making a prediction, every observed value where you actually did run a simulation, the simulation result and the surrogate model result are exactly the same for a Gaussian process model. So the Gaussian process model, what we say is that it interpolates the data. Okay. So what are the bad parts? Well, one is that estimating the parameters for a Gaussian process is technically difficult. If you have points that are close together in space, you may be trying to invert a matrix that's nearly singular. That can lead to numerical instability. Of course, then the model fitting is slow, very much slower than fitting polynomial models. And even though you interpolate the data, if you have a point here and a point here, there's no guarantee that when you're in between those 2 points, the prediction is very close to the real function. And in fact, it may be the case that the kind of bending that you have to do to get your model to go through every data point tends to create artifacts in the model that are undesirable. So that's con number 3, and one that I think that's very important. Finally, the Gaussian process model is based on thinking of the thing that you're modeling as a random function, from the space of all functions, randomly chosen in some sense. And of course, what we're modeling is a deterministic computer model. So there's a mismatch between the theory of the Gaussian process and the actuality of the experiment. That causes me a great deal of cognitive difficulty. So what else might you do to produce surrogate models? Well, one thing, you could just go back to polynomial type regression models, and I'll show you that a couple of times in the rest of the talk. Another thing that you could use is neural nets, both of which you would like to use using cross-validation sort of the same way that John Saul did this morning in some of his modeling. Here's the internet simulation tool. It involves 8 factors, which you can either include in the experiment or you can set to particular values. So you can either choose to use all 8 factors in some experiment, or you can make some of them be constant and design on the others. Here's the web address for that, and I think that this presentation will be available afterwards, so you can play with this simulator yourself. one of the things that you see when you click on some of the links in the simulator is a picture of this sprinkler here, which has various things. There's the pressure going in to the simulator here, and then there's the diameter of this line. There's a couple angles. There's the diameter of the rotor, and these are things that you can change in the simulation. So I want to consider 4 different design strategies to compare. One is the traditional Maximin Latin hypercube. Another is the covering array. Another is a multi-level orthogonal design. And finally, the new fast flexible filling, or triple F designs that are recently invented in JUMP. So let me get started with the traditional design for this is a Latin hypercube design, and the Maximin Latin hypercube design is one of the big competitors for this kind of experiment. Basically, let me first tell you what a random Latin hypercube design looks like. You just take the numbers from 1 to n, and you permute their order. And you do that once for each factor. And then you center and scale them so that they match the ranges that you're interested in. So that's how you make a random Latin hypercube design. If you want to make a Maximin Latin hypercube design, then you have to choose the ordering so that the distances between the points, the minimum distance from any point to any other point, is maximized. So here's an example of a 2-factor Maximin Latin hypercube design that has 11 runs. And you can see there's a kind of pattern that goes. And if you drop every point onto the x-axis, you get an evenly spaced design going from 1 to 11. Remember, I said that you're just choosing the numbers from 1 to n and in a particular order. And the same thing happens when you project onto the y-axis. You just get the numbers from 1 to 11. So in some sense, these designs are evenly spaced in unidimensional projections. One definition of space filling in terms of design is that you want to spread the points far apart from each other in space. By spreading them apart from each other, one measure of that is to maximize the minimum distance between points. However, another kind of way of thinking about space fillingness is that pick some point in space, like this one here, and measure the distance between that point and the nearest design point, and find a design that minimizes the distances of arbitrary points to a design point. That's called a minimax design, and that's much, much, much harder to produce. So nobody tries to do it. It's a exponential time kind of problem. So even though that's a more desirable thing to do, it's not what people tend to do. So the properties of the Maximin Latin hypercube design is that the design points are equally spaced for each factor, and they don't replicate themselves in projection. And that's a good thing because when they don't replicate, replication is useless in deterministic modeling because a replicated point doesn't convey any information. And if you have a Maximin Latin hypercube design, then the design points are spread out more than they are for any other Latin hypercube design. So John briefly introduced the covering array in his talk, John Saul, and that technology is courtesy of Joseph Morgan, so I'd like him to stand up for me, please. He needs to be embarrassed, please. Joseph is a world-class expert in this technology, And as you could see from the brief demonstration that John gave, he actually set the world's record for the TCAS problem and broke it by a lot. And the implication of that is that for testing systems where each system test is complicated and expensive, he could save testers millions of dollars as a result of that kind of advance. So I'm gonna use a covering ray, but not in the sense of system tests, but actually in a data analysis sense. And I'll show you that as one of my examples. In version 11, we created a new kind of screening design, and I'm calling it a multi-level orthogonal design. It's in the screening platform, the screening design platform, and that work is the responsibility of Ryan Lekovitz, who is sitting next to Joseph Morgan, and he's going to have to stand up too. Ryan sent me a paper with this methodology. I'm the editor of the Journal of Quality Technology, and I read the algorithm, his algorithm for generating these designs, and I immediately made them. I coded it up myself, dropped it into JMP as a starting design generator for the custom designer, and then I rejected his paper. Well, I rejected it with encouragement to revise, and it's taken a long time to revise it, but it's finally accepted, and it'll be appearing in the next while so the competitors can catch up. All right, and then the latest thing is this fast flexible filling design. That's new in JMP 11 as a space filling design tool, but we also have made improvements based on this idea of MaxPro, which is an invention of a professor at Georgia Tech, and I'll talk a little bit about this criterion. Here's the MaxPro criterion, which basically is a double sum of a product of reciprocals. So N is the number of runs that you're going to do, P is the number of factors, and if xij is, or if xil is, and xjl gets small, then this product is going to get really big. So what you want to do is make m here, this m here, be small. If you do that, what you're doing is forcing the points apart from each other. But the cool thing about this criterion is that it spreads points apart in one-dimensional projections, two-dimensional projections, three-dimensional projections, and so on. It does a good job of spreading points out regardless of the dimensionality that you end up with when you do your analysis. So this MaxPro criterion, I think, is a real breakthrough, particularly in terms of the computation time to generate designs using this. So here are the optimal settings using the fast flexible design for this garden sprinkler application. So with my remaining time, what I want to do is move away from PowerPoint, which John would probably prefer that I didn't use anyway, and go directly to JMP and show you JMP and the garden sprinkler application, and use some of these designs to generate data, show how to model, and try to understand the comparisons of the various approaches. So that's my plan. And here is the internet tool. And one of the things you can do is, if you click on this global configuration, you can either run the tool with added noise or not. And I'm making it where it doesn't have added noise, so it's a deterministic simulator, but you can make it a physical simulator. You can also choose to not only measure range, which is the distance that the water sprays out, but you can measure the consumption and the speed of the sprinkler as two other variables. So you can model three things at once. So I remove the noise and only look at range. And then this is the description of the factors, which I talked about a little bit. So here's my journal, and the first thing I want to do is look at the Maximin Latin Hypercube design. Well, one thing I can do is just show you how to build it in JUMP. You go to the space-filling designs, and you load in your factors, and here are all my 8 factors. And then I can specify how many runs I want to do, and click Latin Hypercube, and it will generate the Maximin Latin Hypercube design. So that's all it involves. I have this design without the response data, and all you have to do to use this simulator if you have JUMP, and God bless the guy who built this simulator. He made it so easy. All you have to do is copy the data and then go down here and paste it in. And then click the calculate button. And oops, I must have selected more. They're all in the design. One thing that I don't like about this is if you mess up, then the global configuration changes. 1, 2, 3, 4, 5, 6, 7, 8. Should work. And then I save this into my desktop. And so now I have a table that has my responses in it. So now here's my Latin Hypercube design, and then I have a little JSL script that imports the responses into the design. So that's just how easy it is to do. And here's the same design, just to show you I'm not cheating. This is the same design, and you can see that the responses are matching up point by point. It takes over a minute to fit the Gaussian process model for this, so I don't want to waste the time to do that, but here's the result. And these points here, if you had a perfect fit, perfect modeling, they would all follow on a 45-degree line and there wouldn't be any variation. What you're doing here is you're leaving one point out and then predicting it with the rest of the points. And so it's not, when it's left out, it's not in the data set, so it's not being predicted perfectly. So this is an indication of how well the model is fitting. And this is a profiler that shows the prediction at the maximum range of using the Latin Hypercube design and Gaussian process modeling. So I can remember these settings, and I can right-click on this and make it into a data table, and then I can go back and see how close so the predicted range is 7.57, and the confidence interval on the range goes from 7.31 to 7.84. So let's see how close we are when we actually run the simulator at that point. So I'll go back here. And just paste these 1, 2, 3, 4, 5, 6, 7, 8 values in. And I get 7.96, which is it's bigger. That's a good thing, but it's also outside the confidence interval. So why? Well, number one, the model that we're actually trying to model is not a Gaussian process. So the confidence intervals that you make using the assumption of a Gaussian process aren't necessarily meaningful. And while we like the fact that it's predicting a high range here, that maximum is bigger than the maximum it's predicting, it's not doing as good a job as I would like to see modeling the function itself. So it's always mystified me that Maximin, Latin Hypercube designs and Gaussian process models were considered the de facto standard for space-filling designs. And I'm just trying to establish a small seed of doubt in your mind that maybe there's another way that's might be slightly better. But at the same time, I want to demo Jump 12. Okay, so the next thing I want to do is show you the covering array. So I have, here's a covering array without response data, and I want to show you the multivariate view of that data. Notice that the covering array, in this case, turns out to be an orthogonal design. And in every two-dimensional projection, it's showing all the points. So this is perfectly dropping down onto all two-dimensional projections. How did I create this design? Here's the covering array tool that Joseph built. I made each factor be categorical with 1, 2, 3, 4, 5, 6, 7 levels. And then I asked for a strength 2 covering array. So every two-dimensional projection should have 7 times 7 points if you could do that globally optimally. If I hit continue and make the design and then look at the number of points in the design, I see that there are 49. And so this is the globally optimal solution. The best possible strength 2 covering array. And notice that the production of the array is instantaneous. What this array actually is a Hyper-Greco-Latin square, and that was just generated in 0 time, essentially. If I went out, I did the simulation, calculated the range, the range in the way that I already showed you, and if I run a generalized regression, which John also showed this morning, and take the values here, here's the new predicted optimal range, and if I create a data table from this data and pull it into our simulator, we're predicting a range of 7.82, and let's see how we do when we actually run the simulator. I should note that I should note that covering arrays were not created to be space-filling designs, but look at the agreement between the observed range is 7.89, and the predicted range here was, find it, 7.883. So the agreement between the use of a covering array along with a generalized regression tool compared to the Latin Hypercube and the Gaussian process is pretty impressively better, I think. Going to the multi-level orthogonal design, I'll run the design dialog for that. In this case, I could get this by going to the screening design platform and putting in discrete numeric factors that had 3 levels in each factor. So this is, so I have 8 factors, each at 3 levels. If I use Ryan's orthogonal or near orthogonal designs methodology and just use 27 runs, then when I create this design, I have design that is this white space up in the top left corner of the plot. Those are showing that all of the main effects are orthogonal to each other. So this design has found an orthogonal 3 to the 8 minus 5 design. That's and again, you can see how fast the design creation is. So again, fitting a reduced model from stepwise, I can look at the log worth values, and I can do some model selection, and then run this model, and I get a predicted optimum setting that's very close to the same value that I got for the covering array. Note that the first design that I did was a Latin Hypercube design with 81 runs. Essentially, what they tell you in the literature is that the number of runs that you need to do for a setup that has d dimensions, in this case 8, is do 10 times d run, in this case, which would be 80. So that's the standard advice. The covering array only took 49 runs and gave you a better model. This near orthogonal design, or actually in this case orthogonal design, only has 27 runs. And again, I'm finding a model that's doing a good job of prediction. I think that's notable. Now, granted, there's not a whole lot of nonlinearity going on in this model, but if you've done a lot of computer simulation on your own, you will note that in most of the computer simulations that people run, there isn't a whole lot of nonlinearity, even though that's what you're trying to guard against. Finally, there's this fast, flexible filling design. I should show how that one is generated as well. Again, in this case, I'm doing the 8D rule, and if I make the table for this design, we can look at the values multivariately. And see that they're doing a pretty good job of projecting in 2 dimensions, and also the correlations are reasonably small among the variables. If you look at the one-dimensional view here, you see kind of a small U-shaped pattern in the unidimensional projections. And that is a pattern that was suggested as being useful in a technometrics paper a couple of years ago, basically saying that instead of doing equal spacing, you should actually push points a little bit out towards the edge. Almost done. Let's see how this one performs. Here's the reduced model from Stepwise for this design, and this is the optimum point. And if we make this into a data table and capture all of the values, so the predicted optimal response is 7.94, and I'm observing 8.03, which is also the best, the longest range. If we were trying to maximize the range, we've now found the best range so far among all the design analysis approaches, and it was. We did pay more than we paid for in terms of the experiment. We paid more than the covering array. We paid more than the orthogonal design. We paid the same amount as we did to run the Latin Hypercube, but we got substantially better results. I think the jury's still out on what the best possible design analysis combination is for doing computer simulation modeling. What's nice about JUMP is that you have a lot of choices for the analysis. You also have a lot of choices for the design. Once you've chosen a design, though, now all you have left is choices for the analysis. But being able to do the generalized regression, Gaussian processes, neural nets, or various kinds of cross-validated polynomial models gives you a lot of flexibility and a lot of ways to compare models to decide what you want to do in terms of sort of settling on a model. And thank you for your attention. I really enjoyed this talk. Yeah.
Thank you, Brad. I know Brad will be very happy to take questions. I just want to make one comment, if I could, because in my mind, the word primer conjures up kind of a rehash of stuff that's out there in the literature, and it's kind of a getting started thing. But I think you'll agree that what we saw there was very innovative and even groundbreaking. So thank you, Brad, and ask the questions, please. I think you can use the microphones on the desk in front of you. So if you could state your name and affiliation first, that would help.
Hello. Thank you, Brad. That's a great talk. I have a question. So you said that in covering array and generalized regression, you chose 7 levels, and you made the factors discrete numeric. And then when you did the multi-level orthogonal design, you did 3 levels of the discrete numeric. How do you make those choices?
Well, for the purposes of the talk, I made the choices so that they were different, because I wanted to just point out that there were different things you could do. Your choice of how many levels that you make for each factor in a Latin Hypercube design, you use, if you have n runs, you have n levels. If you that's a requirement of the design. Do you really need n levels? Are you really getting what you think you're getting by using as many levels as there are runs for every factor? I think not. I think the choice of the number of levels is related to your a priori notion of how wavy the underlying response is with respect to each factor. If you think the underlying response is very wavy, then you need a lot of levels. Jose.
Hi, Brad. Thanks for whetting our appetite and giving us all these new choices. I was wondering if we can step back a little bit and you can comment on the type of designs that we can use when developing the deterministic model or refining the mechanistic model. And number two, the designs to use once you have the mechanistic model and you want to qualify it or validate that with real data.
If you, let me deal with two first. If you had a simulation experiment and a polynomial model that came out of the simulation experiment, you could use the augment designer in JUMP and make the first set of runs be the physical runs and the second set of runs be the real runs, and then look at interactions between that categorical factor and the factors in the experiment, and that would give you a feeling of how well the physical experiment was matching the computer simulation experiment. In terms of validating mechanistic models, that's a whole research area. In JUMP 12, there's going to be a space-filling augmentation capability, so that when you do go into augment design, one thing that you can choose to do is augment the design in a space filling such a way that the new points are chosen to be away from the old points, so that you get an idea for validation.
I had a question. I noticed that for your input variables, you use categorical, but then on your fit, they were obviously numeric. I was wondering if you could speak a little bit to that.
I use categorical variables in the covering array because covering array technology basically assumes that you can describe all your variables as having a fixed number of levels. But then, since I'm using this experiment in a different way from what covering array sort of was built to do, instead of testing systems that have zero error, I was actually trying to map a multi-dimensional response surface. I changed all the categorical variables to be continuous over the range that they were made, and. So I was using a technology in a way for which it wasn't intended, but in a way that sort of demonstrates that even though you do that, sometimes very nice things can happen.
Brad, just to clarify, did you the models that you used for each one of these, were they all second-order polynomial models?
In some cases, I actually considered higher order than second order. I think in the fast flexible filling, since I had more runs, I think when I did the stepwise, I included all the third order terms as well. So one thing about having multi-level designs is that you can fit much higher order models, and if the data justifies it, then you can pull those kinds of terms into the model to use for prediction. Stan.
I noticed that on the things when you went through, certain variables had a flat response, implying they had no effect. Did all four models tell you exactly which variables have no effect? Did they give you the same answer?
So you can, it's not showing right now, but there's a little bit of a scale problem here because the variables that have a lot of effect are controlling the scale of y. And the ones that have small effect look as if they have no effect, but in fact there is a a real but small effect that's quantifiable. And so, all of the models basically gave you the same 4 variables as the ones that were not very influential. So in that sense, whether you're using Gaussian processes or the various other analytical approaches that we had, and regardless of the design, we were always getting the same qualitatively similar results. The key differences were in the modeling of the alpha, which is the amount of angle that the spray was going up.
Okay, well, thank you. If there are no more questions, please join me in congratulating and thanking Brad.